Math is everywhere around us. It is in the sports we play, the nature we observe, and inside of us. It is moving and controlling everything seamlessly. Whether we have created math or discovered it, there is no doubt that it is everywhere. So, how is it used in the Olympics?
Казвам се Тихомир Иванов и съм състезател по лека атлетика. Участник на 2 олимпийски игри. Като професионален спортист смятам, че математиката има изключително голямо значение в спорта. В леката атлетика намира голяма приложност, когато се пресмятат разстояния, бягания, времето, което трябва да се пробяга една дистанция, също така ъгъла, под който трябва да се отскочи за дадена дисциплина или да се хвърли даден уред. Така че смятам, че математиката има доста голямо и пряко значение в спорта и в леката атлетика. Поздрави!
We start with performance analysis and grading. Especially in gymnastics, math plays a huge role in determining the score of the performer. The score is usually divided into two parts, one for difficulty and the other for execution, and then they are combined for the final score. Math is also used in tournament brackets, especially in tennis. In order to determine the tournament placements, the organization usually uses seeds, which are basically points for performance in past tournaments. Third and final use we are going to explore today is the usage of math in shot analysis. In sports such as the javelin throw and the shot put, there isn't much room for improvement, and in order to improve the past records, you will need to have a pinpoint and perfect performance, which is only possible through shot analysis. Is there a perfect throw? A throw without error, without any room for improvement. The absolute shot, where they could be by analyzing the most fundamental segments of the throw, such as its release angle, release height, speed, and whatever else composes of the throw. Before we observe the perfect throw, we need to clear some things out. Every thrown object follows a path called a trajectory until it hits the ground. The object is thus called a projectile. The trajectory is affected by gravity, which equals to negative 9.8 miles per second squared, while the projectile is affected by multiple factors including gravity, angle and speed of the release, height and air resistance. As we can observe the graph, the trajectory of an object can basically be presented as a parabola which reaches a maximum point. The height and length of the parabola will be determined by many factors, most important of all being the angle of release, which we'll get into further. The final point we need to make before analyzing the perfect shot would be that horizontal and vertical motions are independent of each other, which means they can be analyzed separately. The shot put. In shot putting, the athlete tries to project the shot as far as possible while remaining within the confines of the throwing circle. During the flight phase, the shot is essentially a projectile in free flight, and so its trajectory can be accurately predicted given sufficient information about the release conditions. Shot putting requires great explosive strength together with the ability to perform precisely timed movements in a confined space. The athlete's objective is to project the shot as far as possible, but competition regulations restrict the technique that may be used. The shot must be thrown from the shoulder using one hand, and it must be held near to the chin throughout any preliminary movement. Throughout the throwing motion, the athletes must remain within a circle of 2 meters diameter that has a 10 cm high stop board placed at its front edge. The shot is a relatively heavy implement, 7.26 kg for men and 4 kg for women, and unlike the discus and javelin, it does not have any special flight enhancing features. The shot will thus require more physical strength and travel less distance from the javelin or discus. Shot put performance is quantified by the official distance, which is the distance from the inside of the circumference of the throwing circle to the nearest mark made by the fall of the shots. The official distance may be considered as the sum of the release distance, the flight distance, and the landing distance. Release distance is the horizontal distance from the inside edge of the stopboard to the center of mass of the shot at the instant of release. The flight distance is the horizontal distance the center of mass of the shot travels from the instant of release to the instant of landing. The landing distance is the horizontal distance from the center of mass of the shot at the instant of landing to the mark on the ground nearest to the throwing circle. In most throws, the flight distance is almost equal to the official distance. The radius of the shot is relatively small, and so the height difference between the release and the landing is approximately equal to the release height. The flight distance of a shot in free flight is given by the formula below, where v is the release speed, O is the release angle, and G is the acceleration due to gravity. For shot putting on level ground, the landing height is equal to the radius of the shot, which is about 6 cm for men and 5 cm for women. When shot putters throw with a high release angle, they are opposed by a greater effect of gravity during the delivery phase, and so the release speed of the shot should be reduced. To achieve the greatest possible flight distance, the athlete must project the shot with the optimal combination of release speed, angle and height. Release speed is strongly correlated with the throwing distance and is without a doubt the most important factor. It is instructive to show in a graphical form the application of the equation to the flight of a shot. The figure shows the effect of changes in release angle on the flight distance of the shot. Curves are shown for a range of release speeds from a value that produces a modest flight distance to a value slightly greater than that produced by a world-class shot putter. The calculations are made with h equals 2.10 meters, which is representative of the height difference for a world-class shot putter. The radius of the shot is relatively small, and so the height difference between the release and the landing is approximately equal to the release height. The graph shows the effect of changes in release height on the flight distance of the shot. Curves are shown for a range of release heights from a value that would be expected for an athlete about 1.50 meters tall to that for an athlete about 2.20 meters tall. A higher release height produces a greater flight distance but at a slightly lower optimal release angle. In the shot put, release speed is considered more important than release height because changes in release speed have a greater effect on the flight distance than equal relative changes in release height. At the instant of release, the athlete is assumed to be standing upright as shown in the graphic. The athlete has the throwing shoulder raised so that the line of the shoulder is aligned with the throwing arm, and the angle of the throwing arm to the horizontal is the same as the release angle. The expression for the height of the shot at the instant of release is the first formula, where H shoulder is the height of the athlete's shoulder when standing upright, and L arm is the length of the athlete's outstretched throwing arm and shoulder. When shot putting on level ground, the landing height is equal to the radius of the shot, and so the height difference between the release and the landing becomes the second formula, where R shot is the radius of the shot. The graphic shows a model where the shot putting action is reduced to just the delivery phase. The athlete applies the shot with a force at an angle to the horizontal. The combined effect of the applied force and the weight of the shot is the resultant force that produces acceleration of the shot along a straight line path at an angle to the horizontal. This acceleration path is at the same angle to the horizontal as the release angle. According to data presented in Winter Olympics 1990, the height of the shoulder when standing upright is 81% of the body height, and the distance from the midpoint of the shoulder to the tip of the outstretched arm is 57% of the body height. For a projectile that is released with constant speed from ground level, the optimal release angle that maximizes the flight distance is 45 degrees. However, in shot putting there are 4 additional effects that substantially modify this optimal release angle. So what was learned after all these equations and graphs? Well, math helps in analyzing shot put performance, but as far as the perfect shot goes, it is something every athlete must find for himself. The Olympics are coming and new and strong players are emerging. Strategies are evolving, players are more knowledgeable than ever. But how does the knowledge of mathematics help us gain insight into the world of tennis? Every week the Men's Association of Tennis compute and update the world rankings for professional tennis players. They do this by awarding points to every player, then ranking players from fewest to most points. But how are the ranking points calculated? Each player's best tournament results of the last 52 weeks are selected and points are awarded for each tournament based on the type of tournament and how far the player progressed before getting eliminated. Once the players are ranked, seeding a tournament can just be a matter of listing the top 32 entrants in order of ATP rankings. This is how the Australian Open, French Open and US Open tournaments are seeded. Wimbledon, however, chooses to do things a little differently. Instead of using the ATP ranking points, they use their own modified points calculated using this formula below. How exactly are tournaments structured? How do none of the top players ever face each other early on? Well, this is the process. Once the top players have been seeded, there are two main considerations that determine how tennis tournaments are structured. First, the number of matches needs to be kept to a manageable level. Grand Slam tournaments, for example, start with a field of 128 players, so let's go with that. The reason this specific number is chosen is because it is a power of 2, which allows all players to be able to play out their matches without waiting for another opponent to finish. But what is the fewest number of matches that we need in the tournament? If we assume that a player has to lose at least one match in order to be knocked out of the tournament, then no matter how we structure the tournament, we're going to need at least 127 matches. That is because we're starting with a field of 128 players, and 127 of them have to be knocked out before we can determine the winner. Can we design a tournament that determines a winner after precisely 127 matches? Yes, we can, and it's surprisingly straightforward. We use what is called a single elimination tournament structure. This tournament features the mathematical process of exponential decay. Half the players that start any given round are knocked out by the end of that round, which causes the number of players left in the tournament to drop off rapidly as the tournament progresses. The winner and runner-up of the whole tournament only need to play 7 matches, and every other player in the tournament plays fewer matches. The tournament is also designed to get harder as time progresses due to better and stronger players facing each other, but in order for that to happen we need to structure the tournament in such a way that stronger players won't meet each other in the early stages of the tournament. There's a very simple solution, and that is to distribute the stronger players to meet weaker players earlier on. We do that by putting the number 1 ranking and number 2 in the very corners of the tournament so they can't play each other until the final. With this logic we can follow further with number 3 and 4 and so on. Likewise, none of the top 8 seeds can meet each other until the quarterfinals, top 16 until 4th round and top 32 until the 3rd. The rest are considered wild cards and are scattered randomly around the tournament. And just like that we have an ideal structure for a tournament which is both entertaining and challenging for the players. This careful setup of tournament draw is why you never see 2 big names clashing until the later stages of the tournament.
My name is Ivan Diamov-Kanev, and thank you for watching my presentation.